wouldn't have to worry about it. So, again, I don't know if you need to jot this down. First off, you're not going to have to know what VSEPR stands for. But remember, valence refers to the outer, so the outer shell electrons. And the R is the important part. The R stands for repulsion. And what that means is my first main bullet point, electrons will be as far apart as possible. So these are bonded electrons and unbonded electrons. So we use all this to determine the shape of the molecule. And hopefully, again, from last class, I tried to emphasize the fact that the unbonded electrons have a greater repulsion than the bonded pair. Because unbonded electrons are kind of on their own on that central atom. Bonded pairs are between two nuclei, so they're held a little bit more in check, if you will. They're kind of stuck between two positive things, so they can't reach out and repel as much. But that unbonded pair, kind of that cloud of electrons on the central atom, that is able to spread out more, able to have more repulsion. Halfway done. My goal next class, when we go over what's called hybridization and sigma pi bonds, is I'm going to give you a little chart that will be able to tie in shape to hybridization as well, and then bond angles and polarity of molecules. So we're spending, a fair amount of time on shape and angles here, because if we can get this, we can tie that into what we're going to go over next time. And if you see all those connections, hopefully that makes things a little bit easier for you. So again, 1, 2, 3, 4, 5 shapes are what you're required to know. Carbon dioxide is linear because it doesn't matter if it's a single bond or a double bond or a triple bond. It has 2 bonding domains and 0 unbonding domains. Like I believe on your website, it gave you a 2-atom molecule and asked you to identify as linear. It's kind of weird to identify something that always has 2 atoms as linear, but I guess it works. It is just a straight line still. Trigonal planar. Again, you've seen this on the activity that you just did. Maybe it'll help if I remind you as well that this bond angle is 180 degrees. Trigonal planar, I'll draw that up here. And I'll try to represent that 120 degree angle. But remember, if you don't draw it as the shape is, that's okay. You can draw on right angles. I think I saw Tyler before had something kind of drawn at a right angle, but if you can then at least still identify what the angle is, you're in good shape. And that is one of the ways that they will, on tests, kind of trick you a little bit. A very common trigonal planar would involve carbon double bonded to oxygen, and then 2 more things coming off of it. Okay, carbon chains, very common in things. Methane is CH4. That's what comes out of our natural gas jets when we light our Bunsen burner. Here's another one that, when drawn out, makes you believe that that bond angle is 90 degrees, when in fact it's more like 109.5. Because in 3 dimensions, they can spread out a little bit more than in 2 dimensions. But there's limitations to how we can draw things 2D. So these first 3 shapes are the shapes that do not involve unbonded pairs of electrons on the central atom. Doesn't matter what's on the terminal atoms, the outside atoms, the ending atoms. Shape is always based upon the central atoms. And as you saw with that packet, you could have more than one central atom if it's a big enough molecule. Trigonal pyramidal, phosphorus trichloride. Phosphorus is bonded to 3 chlorines.
However, phosphorus has 5 valence electrons to start, just like nitrogen, just like arsenic. Because of that, it has an unbonded pair on that central atom. And the entire VSEPR theory is trying to relate the fact that even though this has 4 domains like tetrahedral, that bond angle right here is not 109.5. Because that unbonded pair supplies more repulsion than a bonded pair. So usually 107 is the more common indication for that bond angle. So again, we're asking about the angle between 2 of the bonds, not between the lone pair, but that lone pair that's not bonded supplies more repulsion. And then lastly, I'm using water as my example for bent. However, you saw on the packet you worked on, ozone with 1 pair of electrons would also be considered bent. Basically, you're taking something that's linear and you're adding either 1 or 2 pairs of electrons on the central atom. And that is going to stop it from being linear. Again, when we're talking about bond angle, we're talking between these 2 hydrogens is the 104.5. It also has that tetrahedral start to it where there's 4 electron domains. However, 2 of those domains are unbonded pairs, so that's going to add repulsion to it. And as you're hopefully starting to get into that idea of polarity, the last thing I kind of want to talk about dealing with water is why we don't draw it like I did in green. Again, sorry if it's hard for you to see on the bottom, but it's either this or flip back and forth between Smart Notebook and this page. We don't draw water in this linear manner because dipole moments would cancel each other out. A pair of electrons in the top and the bottom would cancel each other out. The OH bond on the left and the right would cancel each other out. And if all of those dipole moments cancel each other out, water would not be a polar covalent molecule, it'd be a nonpolar covalent molecule. And a lot of chemistry would now be turned upside down if that were the case. And the reason why we know water's shape is actually bent and in this configuration on the right deals with all of its properties and how it's able to mix with certain things and not other things, gets into that idea of intermolecular forces, which is what our entire next unit is all about. Phase changes, dissolving, solutions, all that is going to be covered in the next unit. So this is where we're ending with notes, because what you're going to do then is you're going to work on that packet that's dealing with polar and nonpolar.
And to me, the key is the term symmetry. And you guys have worked on these packets enough to know that they're going to start you off kind of easy, but then all of a sudden, we need to be able to look at a molecule and determine, are there polar bonds? Well, that's difference in electronegativity. But secondly, is the molecule polar or not? By the way, on that first page of that packet, if you're having a hard time with some of those shapes that disobey the octet rule, either skip them or just look at my answer key. Okay?